Right, good day, Matrix. Last lesson, video lesson on normal distribution, and today we are going to be using normal distribution to approximate a binomial distribution, because sometimes it's just too much of a mission to use a binomial distribution. And the only person who's prepared to come in today is Nicole. She says she's not really into watching videos, so she'll at least participate in one of them. Say hello, Nicole, everyone. Yes, lovely. All right, lob her out the way. Okay, right. So switch screens. And we want to go here. Okay. All right. So just before you go to your notes, which you're going to have to use later, just a quick reminder of what a binomial distribution is. Okay. So it's used for discrete data, so in other words, not continuous data. So an exact number of events has to happen, like 1 or 2 or 3, not like time, 10,213 seconds. Okay. Then it's called bi because there are only 2 possible outcomes. Okay, either one a success or failure, and then the outcomes are mutually exclusive. In other words, it has to be the one or the other, and they're independent, and those kind of things go together. Probability remains fixed. So, you know, whether you spin a coin once and you spin it again, okay, spinning it before doesn't change the probability the next time around. So that was one of the distributions we did together with the hypergeometric for binomial distributions. And the formula we have is that the probability x is your random variable, the probability of getting x number of the event is equal to, so x is equal to ncx, p to the x 1 minus p to the n minus x. That's on your formula sheet, where n is the number of possible trials. So if you throw a coin 50 times, that's n. P is the probability of success. So if there's a netball and you had 20% chance of scoring, p would be 0.2, and then 1 minus p would be probability of failure, which would be 0.8. And then x is the value. So in other words, if you have 30 shots at netball, if you want to figure out what's the probability of getting 13 goals, then you replace x with 13. That's your random variable over there. In a binomial distribution with discrete data, this is what your probability distribution looks like. Okay, probability distribution is like that because they're discrete. So in other words, if you had a chance of no goals, 1 goal, 2 goals, or 3 goals, it'll be something like that. But in a normal distribution, where we're working with continuous data, here's your probabilities, and here's your x values over there, and it forms a normal curve. And remember that for one individual score, the probability of x is equal to 0. In other words, the probability of running a race at 42 minutes 15.03421 seconds, any probability is so small that it's effectively naught. So that's why in normal distribution, we don't look at individual scores, we look at regions. Okay, because the probability of an individual score is equal to 0. Right, before we go on to using a normal distribution to approximate binomial distributions, okay, let's just try the exercise I asked you to do. And it comes from page 33, number 1 and number 6. And question 1 says, if a fair coin, okay, so straight away the word fair coin tells us the probability of getting, okay, let's just read the whole question. If a fair coin is flipped 5 times, what is the probability of getting exactly 3 tails? So remember, with these questions, you should define x. So we defined x as x is equal to the number of tails, okay, because the event is that you want to get tails. The probability of getting a tail is 0.5 because it's a fair coin, okay, and n is the number of times you throw the coin, so n is equal to 5, right? So, and the question is, what's the probability if you throw a coin 5 times that you're going to get 3 heads, 3 tails, right? So we're going to use a formula, probability x is equal to ncx, p to the x 1 minus p to the x. So the probability that x is equal to 3 is going to be equal to, we're looking for 3 heads from 5. Okay, you could use your Pascal's triangle for that. P is equal to 0.5. So it's going to be 0.5 to the x, which is 3. 1 minus p then is also going to be, if p is 0.5, 1 minus p is also 0.5. And this should be n minus x. and n minus x is going to be 5 minus 3, which is 2. You chuck that all into your calculator, and you get 5c3 times 0.5 cubed times 0.5 squared, bollocks, times 0.5 cubed times 0.5 squared, and I got an answer of 0.3125. 0.3125, which is the same as the memo. Fantastic. Right. So that's one example of a binomial distribution. Right. Then question 6. Question 6 says, police records have shown that 35% of drivers are drunk on a certain roads at night, but assume that the police randomly and independently stop 10 drivers. What is the probability that no driver is found drunk? That's question A. So P, if we let X be equal to the number of drunk drivers, P is the probability of somebody being drunk is 0.35. Okay. And then N is the number of people that they test. So N is equal to 10. And so we're looking in the first one, we want to know what's the probability that X is equal to 0, that they don't catch any drunk drivers. So using the formula again, using this formula over here, the probability that X is equal to 0 is going to be equal to, I want none from 10. Probability of being drunk is 0.35, so P is 0.35. Okay. To the X, which is 0. Okay. 1 minus P, which is 1 minus 0.35. To the N minus X, which is going to be to the 10. If you log that into your calculator, well, you get 10 C0, okay, times, well, that's 1, that's also 1, by the way. Okay, so it's going to be times 1 minus 0.35 to the 10, and we get an answer of syntax error. Hang on, it's just 1 minus 0.35 to the 10. And you should get 0.0134. So approximately 1.34% chance that none of the drivers are going to be drunk. Okay? Right. So that's your first one over there. The next one says probability that exactly 4 are drunk. So the probability that X is equal to 4 is equal to you choosing 4 from 10, 0.35 to the 4, 1 minus 0.35 to the 6. And if you chuck that into your calculator, I'm going to cheat a bit and have a look. You should get 0.23767. 0.23767. Right, so that's the probability of getting exactly 4 drunk drivers caught. 0 was equal to that. And probability of at least 1, remember, is going to be 1 minus the probability of none. So it's going to be 1 minus 0.0134, which should give you 0.986. Okay. Right, so that's just a recall of what binomial distribution is. Remember, when I use binomial, independent, mutually exclusive, just 2 possible outcomes. Okay, and it's for discrete data, right? So that was page 133, number 1 and number 6. Right, now I'd like you to go to your notes and to page 191. Right, so we're going to try fill in these notes on page 191. You can fill them in with me, or you can go back and do them by yourselves. Okay, but try be proactive. So remember, binomial distribution is a discrete distribution. Now, under certain conditions, it's a mission to use a binomial distribution. There's just too many calculations. So under certain conditions, I can use a continuous normal distribution to approximate that binomial, right? And don't worry about the continuity corrections yet. So just a quick recall of notation. If you've got a binomial distribution, the way we represent it is you've got a set of random variables. There's your formula, which we just discussed. N is the number of outcomes, P is the probability of success, so that's N and P. Okay, and for a normal distribution, which is for continuous data, so binomial, strictly speaking, is supposed to be for discrete. Normal is supposed to be for continuous. Okay, and the notation we use is you've got a random variable with a mean of sigma, a mean of mu, and the variance over there. Right. So also remember that the mean, well, just think of this. If you have 1,000 coin tosses, okay, so you toss a coin 1,000 times, okay, and I said to you, what is the mean expectation of the number of heads? Well, to find the mean, what you'd expect to happen, okay, the most likely outcome would be 1,000 times 0.5. Okay, the number of times you throw the coin times the probability of the event happening. So in other words, the mean of binomial distribution, and we're going to be using this now, okay, mu is going to be equal to NP. And we're going to use this calculation, okay, to find we're going to, if the conditions are hold that we can use a normal approximation for binomial distribution, that's how we're going to find mu of the normal distribution as well for the approximation. And we're also going to have to, if you're using a normal distribution, you have to know the standard deviation. Okay, and we're going to find the standard deviation by using the binomial distribution for the normal. And your formula is NP for sigma squared for the variance, NP 1 minus P. So in other words, what we're normally going to use is the standard deviation, which is going to be the square root of NP 1 minus P. And in calculations, when we use the normal distribution, always leave it in third form unless it's a nice number. So conditions for using the approximation. So now we can only use an approximation to work out binomial distributions. We can only use the normal curve if two conditions hold. Okay, and the first is that your mean has to be bigger than 5. In other words, NP of your binomial must be bigger than 5. Okay, and what I call the mean of the non-event. So that was the means of scoring a goal. This would be the mean of not scoring a goal. So it's N times, I call that mean of the non-event. N times 1 minus P must also be equal to 5. So both of those conditions have to hold. Otherwise, what's happening is your normal distribution, your binomial distribution doesn't look like a normal distribution. So we can't use the normal to approximate binomial values. This will always happen. You normally can use it if n is very large, no matter what the probability is, and when p is close to 0.5. So when your probability is around 0.5. Okay, let's have a look at page 192. Okay. Right. So when something is not close to 0.5, so it's not close to 0.5, so say there's only 20% chance, for instance, say there was a 90% chance that you, I don't know, scored a goal in the binomial distribution. Okay, then say we had 10 throws, the highest would be around about 9. Okay, so and then it would go down like that. That would be a 90%. That if there was a 90% chance, okay, that you scored a goal, okay, if p was equal to 0.9, and you had like 10 throws, that's what your distribution would be like. Okay, it would be skewed to the left, right? And you couldn't really fit a normal curve on that because it's unbalanced. So a normal curve would go here, and it doesn't approximate that over there, right? We'll see it more clearly over here. So, however, even if you've got a bit of a weird probability that's close to 1, like 0.9, or in this case, close to 0, like 0.2, for a small sample space, okay, it's not going to look like a normal distribution. But once the sample space gets bigger and bigger and bigger, then no matter what your probability, any binomial distribution starts to look like a normal distribution. It starts to approximate a normal distribution. So that's what that says over here. And what we're illustrating here in green is when n is large enough, okay, no matter what the probability, the binomial tends towards the normal, right? So if I looked at this thing over here with some sample, let's say scoring a goal, the probability of scoring a goal is 20%, right? So p is equal to 0.2, and the girl took 10 shots, okay? If she took 10 shots, the likely outcome is that she's only going to score, most likely outcome is going to be to score 2 goals, right? And it goes less and less and less. The probability of getting 10 is very, very small, right? So if I try put a normal curve onto this, well, it doesn't really work because you've missed out this whole tail here, okay, of the original binomial distribution. So there, it doesn't look like a normal distribution. We're not going to be able to use a normal distribution to approximate the binomial distribution. But we could use our test. So say you've got this over here. Don't worry about, it's not relevant for this. Okay, if I've mu in a binomial distribution is equal to the number of throws times the number of probability of her scoring. So it'd be 10 times 0,2, and 10 times 0,2 is equal to 2. But our condition was that the mean had to be bigger than 5. So it doesn't meet that condition. So even though n times 1 minus p, remember if they talk about nq, that's the same thing as n times 1 minus p. That condition meets it, but this doesn't. So we couldn't, if both conditions don't meet that condition, you can't use a normal approximation. So in that scenario, n is too small. With that probability, we couldn't use it, right? Okay. Just by the way, if your probability had been 0,5, even though only 10 throws, then 10 times 0,5 would be 5, and you could use it because then your probability is close to 0,5. But if your probability is far from 0,5, then you have to have a bigger sample. And even if we took, this girl took 20 shots, then her probability distribution, the yellow one is the binomial, the pink is the normal approximation. If she took 20 shots, well, the mean would be NP, which is 20 times 0,2, and 20 times 0,2 is 0,4. Okay, 20 times 0,2 is 4, sorry. Okay, so once again, I couldn't use a normal approximation. Why? Because NP is less than 5. NP has to be bigger than 5 to use a normal distribution. So once again, there's still going to be a tail. The shape's not going to really approximate it. If I keep it symmetrical, it will look like that. And you're going to skip out all of that bit over there. So it's still not a good enough fit. However, if we take the 100 shots, okay, then what starts to happen, okay, is you start to get a normal distribution. The binomial distribution, the actual discrete data, starts to resemble a normal curve. The normal curve starts to fit on it. So once I get, and the condition would be met here, because 100 times 0,2, don't worry about this for now, would be equal to 20. So that'd be 20, that'd be 80. So here, you could use a normal approximation. Okay, because they're both bigger than 5. But what's going on is that the normal starts to look like the binomial. Right. Okay, I think Nicole's having a nap. Fine, we won't disturb her. Right. Okay, so we're always going to have to check, is NP bigger than 5? Before I do anything else, is NP bigger than 5? Is n times 1 minus p, okay, is also bigger than 5? If both conditions hold, then it's acceptable to use a normal approximation to work out a binomial. And you're only going to do that, they will ask you, use a normal approximation to calculate a binomial distribution. Okay, example 10. And this goes on and on and on, but it's quite useful. So it says a professional darts player has a 60% probability of hitting a bullseye. That's the thing in the middle, for those of you who don't know about darts, that little red thing in the middle. He takes 30 shots at the target. Okay, so first of all, let X represent the number of bullseyes he gets. If they hadn't, X is the number of bullseyes. And it says using the normal distribution as an approximation, okay, to the binomial distribution, determine that. Right. So I would normally start a question like this and say, could you use a normal distribution to work out the binomial distributions below? So I would ask that, could you use a normal approximation? That would be my first question in an exam, to test that you know that. So just to check, in this binomial distribution, well, either you get a bullseye or you don't. Getting a bullseye the one time won't affect the next, so the conditions are all, the events are mutually exclusive, independent, so, and only two outcomes, bullseye or not bullseye. So I could use binomial distribution. Then to figure out, can I use a normal approximation? And just by the way, n is 30, number of shots. P is the probability of X is equal to X, is 0,6. 1 minus P then is going to be 0,4. Then I'd say, could we use a normal approximation? Well, I can use a normal approximation. What are my conditions? NP has to be bigger than 5, and N1 minus P has to be bigger than 5. Both of those have to hold. So in this case, N is equal to 30. P is equal to 0.6, and 30 times 0.6 is going to be 18. Okay, so that's 18, which is bigger than 5, so that meets the conditions. And then 30 times n times 1 minus p will be 30 times 0.4, which is going to be 12, which is also bigger than 5. So therefore, you can use a normal approximation. Okay, so you can use a normal approximation in this example. If you did all the individual binomial distributions, this is what it would look like. So the most likely outcome you would get is 60% of 30, which is 18, right? So 18 would be the most likely outcome. Okay, and to use a normal approximation, the first thing you're going to have to do is you're going to have to find mu. You're going to say to yourself, what's mu? What's the most likely outcome, which is the mean. Okay, and to find that this is the mean over here, you can see it graphically. That's the most likely outcome. The mean of a binomial distribution is the most likely number of the event that you're going to get. So before I can use a normal, you've always got to first calculate mu, what we're going to use in the standard deviation in the normal distribution. So in this case, mu is equal to NP. We worked it over here, which is 30 times 0.6, which is equal to 18. So in our normal distribution, we're going to use mu is equal to 18. We're going to put a normal curve onto here and work with a normal curve. Okay, and my variance is NP1 minus P, which in this case is going to be N is equal to 30, P is equal to 0.6, and 1 minus P is 0.4. So if I go work that out, 30 times 0.6 times 0.4, I'm going to get 7.2. So sigma squared is equal to 7.2. But what we're really going to be, so sigma is stood here, sigma squared is 7.2. But what we're really going to be using, as you know, in a normal distribution, is the standard deviation. And that's going to be the most important thing. So my standard deviation is equal to the square root of 7.2. So those are my two crucial figures. Mu is equal to 18. Standard deviation is equal to 7.2. If you wanted to use the correct notation, you don't have to. The random variables approximate a normal distribution where mu is equal to 18 and your variance is 7.2. But just be very careful. You don't use the variance in a normal distribution. You use a standard deviation. So first thing you're going to do always when you ask to approximate a binomial distribution using normal is check, do the conditions hold? Is NP bigger than 5? Is N1 and P bigger than 5? What that means is that if we could fit a normal curve onto a binomial distribution. Okay. Right. Now in the first question, and you would never, for question A, we're just showing you, you'd never really use, for this example, you wouldn't use a normal approximation. You just go directly. Okay, that'd be more accurate. So in this example, that's just to show you what you do if you did have to do that. For an exact individual amount, for one amount, for probability x is equal to x, no matter what x is. Okay, you just use your binomial. It would be very stupid to use your normal approximation in this case. But they just want to show you that it works and how you would do it if you had to. So if they said, what's the probability? Question A said that they get probability to get 20 bullseyes. Okay, and don't forget in the sum over here, probability of getting a bullseye was 0.6 and n was equal to 30. Right. So we're looking for the probability x is equal to 22. I'm going to use that formula. Okay, so we're going to have n is 30, 22, p is equal to 0.6, x is 22, 1 minus p is 0.4, 30 minus 22 is 8. And you're going to chuck that into your calculator. Okay, and I'm too lazy to, I'm just going to cheat quickly and have a look. And you should get an answer of, where were we? 0.05049. Okay, 0.05049. That's the probability of getting exactly 22 bullseyes, right? So that's how you would do it. For any individual score, it's pointless using the normal approximation Okay, that's what you would do, right? So now we're going to show you that if they did ask you to use a normal distribution to calculate an individual score, which I wouldn't do, by the way, how would you go about doing it? Well, we have to use this principle of continuity correction. So remember, the key idea is this. The probability that x is equal to 22, probability of any individual score is equal to 0. Okay, because it's so unlikely in continuous data of one individual thing happening, of getting a mass of 16,2315243, that any individual probability is 0, right? Individual probs are equal to 0. So in order to get this 22, we're looking at this bar of 22 over here, that in the normal curve, okay, is over here. The area under the curve, remember, is the probability. Okay, and we're going to use the normal approximation, and it's not going to be far off because what it skips out, okay, this is going to be included in the normal, okay, but this isn't, and those two are kind of going to balance out because the area under the curve that's the area under the curve, that's left out, okay, that's included. I don't know if I said that the right way around, but you get the idea. So it's going to be an accurate approximation, right? So here, if I'm using a normal distribution, in order to get the probability of x is equal to 22, which is what I got from the binomial distribution, I'll have to look for the 22 bar approximates the probability that x is bigger than 21,5 and less than 22,5. That's where the 22 bar falls in. So in a normal distribution, in order to work out the probability that x is equal to 22 on a binomial distribution, okay, that's what you'd have to work out. Those two would approximate each other. Okay, but that's what you'd have to use on the normal distribution to get the probability that x is equal to 22. And that's what we're going to do over here. So we're looking for that area between 21,5 and 22,5. That gives us the probability that x is equal to 22. That's how we include the 22 bar. And so first of all, in order to use a normal distribution, we need mu, which we'd worked out. Mu is equal to 18. We used NP to get that. And we need the standard deviation, which was square root of 7,2. Right. So to figure this area out, I'm going to first of all work out this area. Okay. This, okay, here we've got an x score of 21,5. So I'm going to need the z score that goes with that. So I'm going to go z is equal to x minus mu over sigma. X in this case is 21,5. Mu is 18. Okay. Sigma is equal to the square root of 7,2. Okay. And you're going to get z is equal to 21.5. Okay. It's just going to take forever if I don't cheat a little bit. Okay, and if you go work that out, you are going to get an answer of z is equal to 1,68. Right. So it's not, I speak crap. Z is equal to 1,30. So this is the z score that goes with this is 1,30. Right. Okay, that's your z score over there. So the probability to work out the probability that x is bigger than 0 and less than 21,5, I'm going to have to work with this z score over here of 1,30. And if I go to my table, where the hell did I put my table? Of I'm looking for a z score of 1,3. 1,30 is over here, 1,30, which is 0,4032. So what have you worked out? You worked out this pink area is 0,4032. Now I've got to work out this whole green area. Okay, and to work out the green area, I'm going to have to first of all get the z score, which will be 22,5 minus mu, I'm just using that formula, mu is equal to 18 over the square root of 7,2, and you'll get a z-score of, let me cheat quickly, 1,68. So your z-score that goes with this here is 1,68, right? And to work out the probability of the green area, you're going to get your table, look up 1,68, and 1,68 is over here. So it's 0,4535. Okay. 0,4535. That is going to be your, so your green area is 0,4538, whatever it was, and your pink area is 0,4032. So the probability of it occurring in, this is the area that we wanted. Remember, this area over here, that represents the 22. Probability of x is equal to 22 between 21,5 and 22,5. Well, it's going to be the green area. Cut out the pink area. So it's going to be 0,453. What is this? 0,4535. Sorry. 0,4535. That's the green area. Chop out the pink area, which is 0,4032. And if you do that, you're going to get an answer of 0,05030. Okay. Right. And if we compare it, so using the normal distribution, okay, if you can't read my writing, it's in the textbook. Using the normal distribution, okay, we got a solution of 0,05030, and it was pretty close, 0,050, both of them, correct to about 3 decimal digits, nearly 4, okay. But the most accurate in this case is obviously binomial. So for a single individual score, you just use your binomial normally. But if you had to use a normal to get a single score, don't forget it's a region, because the probability of an individual score is equal to 0. Right. I'm not going to past. I'm going to make my limit 40 minutes for this video. Right. B. Next question says, what's the probability that they get 15 or more bullseyes? Now, this is why the normal approximation is useful, because it's a binomial distribution. We're not denying that. But if you had to work out the binomial distribution directly, the probability that you get 15 or more bullseyes, and when he's throwing the dart 30 times, you'd have to work out the probability that he gets 15, probably getting 16, 17, 18, 19, 20, 21, 22, and you have to do all of those calculations, all of these calculations up to 30. And that'd be a nightmare. That'd be the end of your exam. And it wouldn't help you to go at least, okay, because that's also going to be 15 to the left. Okay, so now, okay, we know I can use a normal distribution because NP was bigger than 5 and N1 minus P was bigger than 5, and you could fit a normal curve to this. So now I'm going to use a normal distribution because it's going to save me hours instead of the binomial distribution. But to figure out the probability that X is bigger than or equal to 15, okay, you've got to be careful. To include, here is the 15 bar over here, right? That's the bar that represents the probability. The area of that bar is the probability that X is, that's the 15 bar. And you've got to include, because it's greater than or equal to, you've got to include the 15 bar. Now, if you just went and worked out that directly on the normal distribution, what would happen is you'd leave out, if you started at 15, you'd start over here, and you'd leave out half of this bar. Okay, so your reading would be inaccurate. So in fact, even though they want this on the binomial, on the normal approximation, this is what we call our continuity correction. Okay, for the normal approximation, you're going to have to work out the probability that X is bigger than or equal to 14,5. And remember, that's because 15 is in the middle. Okay, 14,5 is slightly to the left. But if you want the whole 15 bar, you're going to have to work out the probability that X is bigger than or equal to 14,5 on the normal distribution. So over here, okay, again, you can see that you are balancing what you leave out from the area, okay, is compromised by the extra bit that's added in. So that's why it works out quite nicely. So we're going to work out the probability that X is bigger than 14,5. Remember, this is a normal, so if I put that extra thing in, it wouldn't matter, but it does for binomial. So we're going to work out the probability X is greater than or equal to 14,5, like we've always done. So draw a diagram. And if I draw my diagram, don't forget, we've got mu is 18, and we're working with a standard deviation of 7,2. So the first thing you have to do is get your Z scores. These are my X scores. My Z scores, or here would be 0. Okay, this Z score is going to be X minus mu over sigma, which is going to be equal to 14, must be negative, 14,5 minus 18 over sigma, and sigma was root 7,2. And if you put that into your calculator, you're going to get negative 1,30. Right, so this is your Z score, negative 1,30. Right, then what would you do? You'd go to your table and you'd look for a Z score of 1,3, and a Z score of 1,3, we just did that just now, is 0,4032. So this area here is 0,4032. Okay, right. So we get 0,4032. So the question was, what's the probability that he gets at least, I think it was, at least 15 bullseye? Okay, that's what's the question. So we're looking for this is the area we're concerned with. This is the probability with a normal approximation of getting at least 15 bullseyes. So we know that area is 0,4302. We know this area is 0,5. So the probability that Z is greater than negative 1,3, which is the same thing as the probability X is greater than 14,5, is going to be 0,5 plus 0,4032, which is 0,9032. Let's check if we're correct. That is correct indeed. Okay, so that is, so in other words, you've got about 90,32% chance of getting 15 or more bullseyes, okay, from 30 throws, and that's because he's a very good chucker of darts. Okay, right, that's all what we had to fill in over there. Okay, that's the probability that's right. Okay, so question C on page 197. I think I'll make this the last question, and I'll let you do the others on its own. Right, the question says, what's the probability that you get more than 20 bullseyes? Okay, so now they don't want you to include 20. Okay, don't include 20. So more than 20 bullseyes is from 21 up, right? So 21 up, that's the area that you want, that's shaded in over there. So you don't want to include the 20 bar. So you can't, the correction is going to be, you're going to, in order not to include the 20 bar, you're going to start from 20,5. Remember, 21 is the middle of that bar, 20 is the middle of that bar. So we're going to work with 20,5 over here. So in the normal approximation, okay, to get this area, once again, you can see that balancing issue where you add what you add in, it wasn't there, and what you don't add in balances out. So that's what we're going to work out for the normal. Okay, because in the binomial distribution, the greater than or not greater than matters. Doesn't matter in the normal distribution. To balance it out, in the normal distribution, in order to get just the 21 bar, you're going to work out the probability that X is bigger than 20,5. Again, here it wouldn't matter because that's normal if you included that, but it does matter in the binomial distribution. So we're going to work out the probability that X is bigger than or equal to 20,5. So if I go to 20,5, remember mu is over here. Mu is equal to 18. This is your X scores. Your Z score there is 0. So the first thing you have to do is figure out that Z score, which is going to be X minus mu over sigma, and X is equal to 20,5 minus 18 over the square root of 7,5, and that gives you an answer of 0,93. Okay, so the Z score here is 0,93. Okay, and if you go look up a Z score of 0,93, 0,93 is over here. It's 0,3238. Okay, so in other words, this area here is 0,3238. That probability over here. So the probability that X is bigger than 20,5 or the Z score is bigger than 0,93, okay, it's going to be 0,5 minus 0,3238. 3238, which is going to be equal to 0.1762. All right, 0.1762. Okay, so in other words, what was the question? The probability that he got, I can't remember, 20 or more bullseyes. Right. Okay, I'll do one last one. D. Okay. Now in D it says what's the probability that they're at, in fact I'm going to finish them, it's just D and E, that they're at most 13 bullseyes. So here, at most 13 means you're going to include 13. Okay. So if this was, here's your binomial distribution. Okay, remember 13 is the middle of the bar. Okay, 13 is the middle of the bar. So if you're going to include the whole of the 13 bar, you're going to have to start from 13,5. Okay, in the normal distribution. So for the normal, okay, in order to get probability, include the whole of 13, you're going to have to work out the probability of x is less than or equal to, or probability x is less than 13,5. Doesn't matter how you express it. Okay, so on this curve over here, okay, we're going to have 13,5. That's the area we're going to be working out. Okay, remember it doesn't matter if you have that or you don't have that. So if we draw a little table, we're going to have the normal distribution. If I have my x scores and my z scores, that's 18, that's 0, and I want 13,5 is going to be to the left. So I'm going to go 13,5 over here. I'm looking for this region there. That's the probability of getting, it's going to be pretty small, of getting 13, at most 13, right? So first of all, I'm going to have to find my z-score using the formula, which is x is equal to 13,5 minus 18 over the square root. I'm sure it was 7,2, not 7,5. In fact, I'm thinking all of these are supposed to be 7. Was it 7,5 or 7,2? I apologize. Go back. All of these are 7,2, not 7,5. Okay, wherever you see a 7,5, make it a 7,2. Okay. Right. So 7,2. So 13,5 minus 18 over root 7,2. If we work out that score over there, that z score is going to be negative 1,68. We expect it to be negative because it's, so that's 1,68 standard deviations to the left. So there's my z score. So you're going to have to look up a z score of 1,68, and that's going to give you this area in green over here. And a z score of 1,68 is sitting right over there, which is 0,4535. Okay, so this area here is 0,4535. That area over there is 0,4535. So that, in other words, the probability on the that x is less than equal to 13,5. Okay, which is, by the way, that's on the normal, which is equivalent to the probability that he got x is less than equal to 13 on the binomial, is going to be 0,5 minus 0,4535. And that should give you an answer of 0,0465. Right. So that's the probability that you get at most 13 bullseyes. Right. And the last question, okay, the probability that he gets less than 16 bullseyes. Okay, probability less than 16 bullseyes. Well, again, less than 16 means you can't include the 16 bar. Okay, so I cannot include this bar in pink. That mustn't be in the question. So in order to exclude that, okay, I'm going to go to the left of 15,5. Okay, remember the edges of each bar is 5, right? The middle is the integer. So over here, I'm going to have to work out the probability that x is less than 15,5 because I just want to have probability less than 16. I can't include 16. So you're going to work out the probability x is less than 15,5. Okay, and if I'm just going to squeeze it in over here. Okay, so I want that area over there. There's my x score. My mu is 18. Z, that's 0. My z score is going to be x minus mu over sigma, which is 18 minus 15,5 minus 18 over root 7,5. And if we cheat and use our textbook, I'm going to get an answer of negative 0.93, which it should be negative, it's to the left. So here Z is negative 0.93. Okay. If I go look up a Z score of 0.93, I'm going to get this area over here. And 0.93 Z score of 0.93 is, we've worked it out before, 0.4238. 0.3238. So that area there is 0.3238. So the area we want, in other words, the probability that he gets less than or equal to, he gets less than 16 on the binomial, that's the binomial way we'd write it, on the normal to be less than 15.5, and that's going to be equal to 0.5 minus 0.3238, which gives us an answer of 0.1762. Right, guys, I hope that made some kind of sense. Okay, that is, okay, your normal approximation of binomial distributions. Long video. Whew. Okay, hope you hung in there. Arrivederci. Goodbye. Thanks, Nicole. Not that you just had a nap. I mean, you just had a nap, but still, thanks for coming. Right.